Why was Albert Einstein so adamant on the cosmological constant, that the universe is static, and later he had to delete it from his field equations? What does it say about the scientific community's temperament against the inflow of new and exceptional ideas? One more example could be that of Avi Loeb, who says Oumuamua could be an extraterrestrial object, but he was completely sidelined. P.S. It would be great if you could call Avi to a podcast. He is a great speaker, explains complex ideas beautifully. Okay, interesting. Thank you for the recommendation. Let's see if I can do that. So the question is about the cosmological constant. So what is this cosmological constant? So in 1915, Albert Einstein published his general theory of relativity. In 1905, he published the special theory. In 1915, he published the general theory of relativity. In the general theory of relativity, you have the very important equation called the field equation of general relativity, which relates the mass and energy with gravity, and it replaced the older law of gravitation, which is Newton's law of gravitation. So what you have, according to the Einstein field equation, is that the curvature of space-time is intricately related to the amount of matter and energy that is passing through that region of space-time, right? So that's the Einstein field equation. If you want to understand what the equation is, it says r mu nu minus 1 half r g mu nu is equal to 8 pi g above c upon c raised to 4 times t mu nu. So that is the field equation. It's not a single equation, it's a set of 10 equations. Looks very simple. It's a system of 10 partial differential equations which relate the mass and energy to the curvature of space-time, right? So this set of equations, it matches Newton's law of gravitation for weak gravitational fields. Now what we find, so what Albert Einstein did is that he what he did was he approximated the universe as having a constant density in all directions. So if you look at the universe, it has mass in some places, it is empty in some places, but if you zoom out to very large scales, then you find that it has, you could approximate it as having a constant mass energy density in all directions. So Einstein did that approximation, and he was able to solve the equations for a simplified toy universe with constant density everywhere. And what he found is that the equations, the solutions, they give you something. They will either cause the universe to contract or expand, right? So that's what his equations were telling him, that the universe will either contract or expand. But in those days, in 1950s, in 1915, in maybe in 1920, the the information that we had was that the universe was static. It was unchanging. It was neither expanding nor contracting. Those days, the only knowledge we had was that of the Milky Way galaxy. And we thought, scientists in those days thought that the Milky Way was the entire universe. Right. So that was the scientific consensus. That's what the best observations showed. Now, in the 1920s, Edwin Hubble, an American astronomer, he took he observed that the Milky Way was just one galaxy. There were lots of galaxies beyond the Milky Way, and he also discovered that these galaxies beyond the Milky Way were all getting more and more distant from us. They were all receding from us in all directions, which indicates that the universe is not static, it is expanding. Right? So before this information was available, Einstein realized that his field equations, they would make the universe expand or contract. So what he did was he introduced an additional term, which is the cosmological constant. And what this constant does is that in order to counteract the contraction of the universe, it produces a net outward force. It's like a repulsive gravity kind of force to balance out the contraction of the universe, right? So that's what it did. And later on, when it was discovered that the universe is actually expanding, then he realized that my field equations were telling me this all the time, and I inserted this equation, which with this term in the equation, which may not have been necessary. So he called the cosmological constant that he inserted into the field equations his greatest blunder, right? So that's what he did. It is denoted by the Greek term lambda. Now, in the late 1980s or late 1990s, it was discovered that the universe is not just expanding, but the expansion of the universe is accelerating. The universe is expanding faster and faster. The expansion is accelerating. And this term, the cosmological constant that had been deleted from the field equations, now had to be reintroduced because it represents an anti-gravity kind of force, a negative gravity kind of force that causes the expansion of the universe. So Einstein's greatest blunder actually was valid, right? And that's what we nowadays consider to be dark energy. So nobody forced Albert Einstein to delete the cosmological constant from his field equations. He did that himself because it was discovered. New data came into was new data was made available, and based on the new data, he realized that there was no need for it. But after his death in the late 90s, it was again realized with the introduction of even more data that yes, we need such a term in the Einstein field equations because the universe is expanding and the expansion is accelerating. So that is the story in brief, in rough, about the cosmological constant. Now, when it comes to the scientific community, the temperament against, like Akash says, inflow of new and exceptional ideas, it's always been there. Whether it is the scientists, whether it is any other community, there's always this resistance towards new ideas. Nobody likes new ideas. For instance, we have had this stranglehold of the string theory mafia in theoretical physics for many decades. If you look at the US, most of the funding in physics, in theoretical physics, goes into string theory. So if you want to have a career in theoretical physics in the US, you need to be in string theory these days. It's been like that for a very long time. Nowadays, there are questions have been raised about it and all. So it's always been like that. So there is always this group think mentality. There is always this thinking by consensus, and that's always been there. So, and that's one of the reasons why there's been no new real breakthrough in theoretical physics since 1980. Since since the theory of inflation was introduced by Alan Guth. That was 1980 or 81. After that, there has been no new genuine breakthrough, theoretical breakthrough that is supported by uh, experimental observational evidence since 1980 or 81. So theoretical physics has hit a brick wall because of this groupthink mentality, because of the temperament against the inflow of new and exceptional ideas. And like you say, Avi Loeb said that Oumuamua could be an extraterrestrial object, and the entire scientific community condemned that. Why? It is certainly possible it could be an extraterrestrial alien object, but so there was this very, very strong backlash against this theory, which is perplexing. That's not how you're supposed to behave as a scientist. So you have all these problems in science today.